So we practiced these two AP free response questions in an effort to simulate the 2020 test, where we'll be timed 25 minutes on the first problem and 15 minutes on the second problem. So you can see the first problem is pictured here. It has to do with this graph of acceleration, and we answer these 4 questions about this graph, and I'll attack that on the next slide. So here we go. A car traveling on a straight road with velocity 40 feet per second at time t equals 0. A car is traveling on a straight road. For 0 less than or equal to t less than or equal to 20 seconds, the car's acceleration, a of t, in feet per second squared, is the piecewise linear function defined by the graph. It says above, but I just slid it over here to the right. So here's a of t, the graph of a of t. And in letter A, we are asked, for what values of t is the car's velocity increasing? Well, we're looking at the acceleration, and acceleration is the derivative of velocity. So we essentially need to look for intervals on this graph where the acceleration is positive, right? If the derivative's positive, then the function is increasing. So our derivative is pictured here, and it's positive in this section here. Positive meaning above the x-axis. So in terms of answering letter A, we simply use the graph, and we say the car's velocity is increasing. Sorry, it took me so long to write that. Let's see, on this interval. So this looks like a 3 right there, and this looks like 11. So we'd say something like from 3 to 11 seconds. Maybe more concisely just on the interval 3-11. Something like that. Oops. Usually don't highlight blue with blue. I'll put a little yellow on there. So letter A was pretty straightforward, as long as you understand how to interpret acceleration and its relationship to velocity. We'll attack letter B on the next slide. Letter B asks, at what time in the interval 0-10 is the velocity of the car 40 feet per second? And we're going to justify our answer. Okay, so you'll notice here in the statement of the situation, at time t equals 0, the velocity is 40 feet per second. And essentially what this graph is asking us is to find another time where the car's speed is 40 feet per second, because the interval that we're looking at does not include 0. So we can't just say, oh, it was 40 at the initial time. But we do need to create some sort of an expression for v so that we can figure out when it's going to be 40 again. So because this is the acceleration function, v is going to be an accumulation of change from the time t equals 0 forward. And I'm saying forward because the graph starts at 0 and goes to 20. And we're looking at 0 to 10 for this part of the problem. But I think you'll agree, hopefully, that v of t starts out at 40 and then accumulates change from 0 to a particular, I should put a of t instead of f of t, to a particular time. So this is the function that we're investigating, and we want to know when this thing equals 40 again. Now, we're not going to be able to compute the definite integral with a fundamental theorem because we don't have an expression for a of t, but what we do have is a graph with a bunch of geometric shapes. And so what I can do is I can compute some of these areas. This first triangle, let's see, it's got a 3 for the base and a 12 for the height. 3 times 12 is 36, divided by 2, that's 18, and it's below the x-axis. So this area right here, which I haven't drawn yet, this is negative 18. And then there's another triangle right here. That has a base of 3 and a height of 12, so that's a positive 18. That's up here. We have this rectangle right here. It looks like 3 times 12. That's just 36, and so on, right? We can complete these areas. I'll just finish off this top piece. This is 2 times 6. It's 24 divided by 2 is 12. And so as we're accumulating this area, you'll notice that when we move from 0 to 3, we subtract 18 right here. And then when we move from 3 to 6, we add 18 back on. So we're back at 40 again. So I claim that at t equals 6, v of 6 equals 40 minus 18 plus 18, which is 40, and that is feet per second. And we used accumulation, using accumulation of area. Okay, just going to double check and make sure I completed this thing. As we move forward past 6, all we're doing is adding more area, more positive area. So there's no place between 6 and 10 where we're going to get back to 40 again. T equals 6 is the only place where that's going to happen. So in terms of answering this question, at what time does it happen? It happens at t equals 6 seconds. I guess I should write 6 seconds. And the explanation is that when we write the velocity function using the initial condition and then use area to accumulate change, we end up back at 40 at t equals 6 because the 18 and the negative 18 cancel out. Okay. I'm a little rusty today, but we'll keep going. Let's move on to letter C on the next slide. Letter C asks, on the time interval 0, less than or equal to t, less than or equal to 20, what is the car's absolute maximum velocity in feet per second, and at what time does it occur? Okay. So we said earlier that v of t is this function where we accumulate change beginning with initial condition of 40. I guess I should call this v of x. I probably didn't do that on the last slide. Forgive me for that. Either that or I could call it v of t and change my variable to an x in the definite integral. Anyway, absolute extremes occur at endpoints or critical points. So there are a couple of endpoints that we need to be interested in. T equals 0 and t equals 20. So let's just check v of 0 right now. That's a 40. And then we'll check v of 20 by adding up these areas. Of course, I don't have the picture that I had before. This was negative 18. This was 18. What did we say this was? 36. This is 12. Let's do another one here. Is that negative 12? Yes, it is right here, because this is another one of those 2 by 6 triangles. So this is negative 12. This is another rectangle. 3 times 12 is negative 36. And then, this is 1, 2, 3, 4 times 12 is 48. Divided by 2 is 24. This is negative 24. So if we wanted to do v of 20, we'd do 40. Minus 18 plus 18 is 0. So then plus 36 plus 12 that's 48. Minus 12, minus 36, that's another 48. So this is all 0. I'm just going to put minus 48 right here. So that's 0. And then minus 24. So that's 16. So v of 20 is 16. And then we also have to check the critical points. Critical points are places where the acceleration is 0. So I think you'll agree that we have a critical point at 3 and a critical point at 11. And so we also have to check v of 3 and v of 11. I'll put these critical points in red. V of 3 is going to be 40 minus 18, which is 22. And then v of 11 is, let's see. That's going to be, all the way to 6 is 0. So that's going to be 4. I'm just not going to count the 0. Plus 36 plus 12. That's going to be 88. And that is feet per second. Don't forget, all these are in feet per second. And it looks to me like 88 is the maximum, absolute maximum, because 40, 16, 22, 88 is the highest. And don't forget, we use the extreme value theorem to figure this out. Another way to think of this is we start at 40. For the first 3 seconds, we go negative. So we know we're slowing down. We get back to 40 at 6 seconds, and then we're only adding velocity, if you will, accumulating positive velocity until 11 seconds. From there, we start slowing down again because we go back to the negative side on the acceleration. So intuitively, looking at the graph and seeing where it stops being positive at 11 seconds makes sense. And then in terms of our extreme value theorem, examining the endpoints and the critical points to find out what our maximum value also works. So just keep that in mind, that that's what we were doing. Okay, so 88 feet per second on that one. Let's finish this problem up on letter D on the next slide. In letter D, we're actually asked a very similar question to letter C, except this time we are looking for the absolute minimum in feet per second on that time interval 0 to 20. So we already did all the groundwork for this. We had v of 0 equals 40. We did v of 3, which equaled 22. We did v of 11. That was our max. That was at 88. And then we did v of 20, and that was 16 feet per second. And the extreme value theorem still applies here, right? We have to check, ooh, that's a terrible curly brace, but we just have to check the endpoints of this interval 0, 20 and the critical points. And we have these two critical points again, where the derivative of velocity, in other words, the acceleration is 0. We've tested the values, and 16 feet per second is the lowest one. It's the minimum. And so I don't really need to say much more. We talked a lot about this on the last slide. We've got our minimum. We're done with question 1. We'll go ahead and take a look at question 2 now, and we'll wrap this thing up. Question 2 stated the twice differentiable function f is defined for all real numbers and satisfies the following conditions. F of 0 is -1, f prime of 0 is 3, and f double prime of 0 is -2. And then we have to address these two items here. And I'll do each of those on a separate slide like we were doing question 1. So let's switch over to our next slide and we'll attack letter A. So in letter A, we're told that the function g given by sine of a times x plus f of b times x for all real numbers where a and b are constants. We're supposed to find g prime of 0 and g double prime of 0 in terms of a. And we have to show the work that leads to our answers. Excuse me, in terms of a and b. I think I just said in terms of a there. Okay, so g of x is this thing, right? Don't freak out about these a's and b's. They're just constants, right? They're constant multiples. They tell us that in the statement. And so as we work through our process, we're just going to follow the chain rule, and we'll have extra constants in there. So if I want to find out what g prime is, I'm just going to take the derivative here. The derivative of sine of ax is cosine of ax times a, because of the chain rule. Don't forget the doggone chain rule. So this is a cosine ax. And the derivative of f prime of bx is, f of bx, that's going to be the derivative of f of bx times b. So this is b times f prime of bx. And we were asked to find g prime of 0. Man, I'm just not speaking correctly today. Okay, maybe it's not today, maybe it's every day. And so I'm just going to plug 0 in and see what happens here. So I get a times cosine of 0, because 0 times a is a. So this is a times cosine 0. If you know your unit circle, you know what that is. And this is going to be b times f prime of 0. Because 0 times b is 0. And so as I mentioned, you need to know the cosine of 0. The cosine of 0 is 1. So this piece is just a. And then f prime of 0 is 3, so this piece is just 3b. And when they say find your answers in terms of a and b, that's exactly what we just did. So we're done with g prime of 0. A plus 3b. Now let's talk about that second derivative. G double prime of x. So the second derivative, let's see, this would be, this is a constant multiple a, so don't freak out about that. The derivative of cosine is negative sine of ax times another a. So this is negative a squared sine ax. And again, b is a constant multiple for this part. So this is going to be b squared f double prime of bx. And again, we're going to plug in 0. So let's see if we can do that right down here on the bottom of the screen and not run out of space. G double prime of 0. Again, we're going to have to know our unit circle. A times 0 is 0. Sine of 0 is 0, so that's good. So that all is going away when we do this thing here. And then we've got b squared times f double prime of 0. Remember, they told us what f double prime of 0 was up top, right here. And so this thing is negative 2b squared. And we're done. We're done with letter A anyway. Let me highlight that. So we're using our derivative rules. We're not freaking out about these constant multiples. You do a little algebra to keep track of these variables as you're doing the first and second derivatives, and then you plug in 0 and you use the given information to get these expressions. They said to write our answers in terms of a and b, and that means we're not going to get numbers. We're just going to get expressions. As long as you just have the letters a and or b in there, you're in good shape. Okay, the last piece is letter B on the next slide, and then we're done with this video. In B, the function h is given by h equals e to the negative sine of x times f of x for all real numbers. We're supposed to find h prime of x and write an equation for the line tangent to h at x equals 0. Okay, so first things first, let's do h prime. We're just going to go through our derivative process and see what we can come up with here. Okay, so this is a composition. This is a product, actually. Let's write it out. And then there's a composition inside our product. So this has got all of our favorite rules. The product rule and the chain rule. We used to do this with u's and v's. So that would be u equals sine, e to the sine of x, and v equals f of x. And then don't forget e to the sine of x has a composition. So as you do this derivative, we're going to do, let's do uv prime first. So uv prime would be f prime of x. I don't know why I'm in green right now. F prime of x for the derivative of v times u, which is e to the sine of x. And then we'll do vu prime, so that's going to be f of x times the derivative of e to the sine x. E to the sine x is just e to the sine x, but because of the chain rule, we got to put a negative cosine in there. So this is going to be something like negative, because of the negative for the cosine. No, cosine's positive, I'm sorry. So let's just put plus f of x times cosine x for the chain rule times e to the sine x. There's no negative sign in there. I think I might have mentioned that, but that was wrong. So here's our derivative. We need the derivative to get the slope of the tangent line. So now we're going to do h of 0, because we need to know what h of 0 is, and we need to know h prime of 0, and then we'll have our pieces. So h of 0, we can plug into their given function right here. Sine of 0 is 0, e to the 0 is 1, so this is just f of 0. So this is just negative 1. And then h prime of 0, we're going to plug into our function here. That's going to be f prime of 0, which is negative 1 times e to the sine of 0, which is 1. I'm sorry, f prime of 0 is not negative 1. Come on, dude, get it together. Let's try this again. F prime of 0 is 3. E to the sine 0 is 1. Plus f of x, which f of 0 would be negative 1, times cosine of 0, which is 1, times e to the sine 0, which is also 1. So this turns out to be 2. 3 plus negative 1 equals 2. So my point is 0, negative 1, and my slope is 2. Let's write out the equation for the tangent line. A lot of times we call this L of x. That's going to be f of a, which is negative 1, plus the slope, f prime of a, times x minus 0, which is just x. So this is x minus 0. I guess I'll write that in for now. But really, we would just write this as 2x minus 1. That's going to be the equation for the tangent line at 0 on function h. 2x minus 1. All that work for a 2x minus 1. Okay, there was lots of calculus going on in this problem, and also in the previous problem. Hopefully you just get a feel for what it feels like to spend, 25 minutes and then 15 minutes working on 2 problems. It's a good start for us, but we've got a lot of practicing to do in the next week. So keep up the good work, and you know where to find me if you need me.